All right, welcome to the last video from chapter 4. This is chapter 4, parts 7 and 8, looking at the quadratic formula and the results that you can get from the quadratic formula. So first thing that I want to do, and this isn't something that you'll have to be able to recreate, but I just want you to be able to see where the quadratic formula comes from. So I'm going to start with a very general quadratic equation, just our ax squared plus bx plus c equals 0. And my goal is to solve for x. So if I want to solve for x here, since I don't know a, b, and c, I don't know if I can factor. Since b is there, I can't use the square root property immediately. But as we saw at the end of last class, if I complete the square on this, then I'll be able to use the square root property. So completing the square, I want to divide everything by a. So then I get x squared plus b over a x plus c over a equals 0. Completing the square, I take b over a, divide it by 2, so that's b over 2a, and then I raise that to the second power, so I get b over 2a squared, or b squared over 4a squared. So that's what I want to add to both sides here. B squared over 4a squared plus b squared over 4a squared. So now I have x squared plus b over ax plus b squared over 4a squared plus c over a equals b squared over 4a squared. Now the whole point of that is so that I can factor. My trinomial here is a perfect square trinomial. So I can factor it into x minus b over 2a squared. Sorry, that's a plus. X plus, this is a plus, so this is a plus. And then I'm going to go ahead and subtract c over a from both sides. Equals, in order to simplify my right-hand side now, I need a common denominator. So I'm going to multiply this by 4a over 4a. So that's b squared minus 4ac divided by 4a squared. Now this should start looking familiar. I'm going to go ahead and apply the square root property. Take the square root of both sides only if I put a plus or minus here. So this becomes x plus b over 2a equals plus or minus, I can't simplify the numerator, b squared minus 4ac, but I can simplify the denominator. The square root of 4 is 2. The square root of a squared is a. And then subtracting my b over 2a from each side, I get that x equals negative b over 2a plus or minus the square root of b squared minus 4ac over 2a. Now these have a common denominator, so I can rewrite this as a single fraction. X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So the key here is that I started with any quadratic equation. As long as a, b, and c are real numbers, I can use the quadratic formula to solve for x. Because I did this, I solved this using only mathematical properties, including completing the square and the square root property, which means I can use this for any quadratic equation. So let's see if we can apply it. We have two examples here that we'll go through together. In our first example, we have 2x squared minus x equals 4. Remember, we need this to be in the format ax squared plus bx plus c equals 0, which we said is standard form. So I need to subtract 4 from both sides. So 2x squared minus x minus 4 equals 0. Now I have that a is 2, b is 1, and c is negative 4. I should check if this is factorable just in case. 2 times negative 4 is negative 8. My b value is -1. Can you think of two numbers that multiply to -8 and subtract to -1? Well, 8 is 1 and 8, 2 and 4, that's it. So it's not factorable. I can't use the square root property. I could complete the square, but we just saw that if we complete the square, that's equivalent to using the quadratic formula. So let's go ahead and use the quadratic formula. X is equal to -b plus or minus the square root of b squared minus 4ac all over 2a. Notice every time I substituted one of my variables, I put it in parentheses. This is important so that I don't accidentally multiply when I meant to subtract or accidentally subtract when I meant to multiply. So if you substitute into parentheses, it will help keep track of all of those operations. I'm going to go ahead and start simplifying. 1 squared is 1. -4 times 2 is -8 times -4 is plus 32 divided by 4. So we get -1 plus or minus the square root of 33 over 4. Now, because of that plus or minus, this is still two solutions. And these are real numbers. So I can say these are two real solutions. Let's try it again on part B. I have x squared plus 6x plus 9 equals 0. And I say, okay, well, numbers that multiply to 9 and add to 6 are 3 and 3. So this one I don't need the quadratic formula for. I can write this as x plus 3 squared equals 0, which means x should equal -3. If x plus 3 is 0, let me write in that step. If x plus 3 is 0, then x is -3. Okay, let's try it using the quadratic formula to make sure we get the same answer. A is 1, B is 6, C is 9. X is equal to -b plus or minus the square root of b squared minus 4ac all over 2a. So we have -6 plus or minus the square root of 36. 4 times 9 is also 36 divided by 2. This is nice because 36 minus 36 is 0. So I have -6 plus or minus 0 over 2. And what we have here is that if I take -6 plus 0 and -6 minus 0, that's the same thing. Really what we have here is just -6 over 2 or -3. So notice when the thing inside of the square root, the value underneath the square root equals 0, I ended up with only one real solution. So we talked about this a little bit last class. We don't always have to get two solutions for a quadratic equation. The solutions, the zeros, the roots, they mean the x-intercepts. And we've seen that we can have parabolas that cross the x-axis. We can have parabolas that touch the x-axis. And we can have parabolas that don't cross the x-axis. So something like this would have two solutions. Something like this could have one solution. And something like this could have no solutions, right? And it's not about whether it's opening up or down, it's about where it is with respect to that x-axis. So I'd like you to go ahead and try two of these on your own, just using the quadratic formula if you need it. If you can do it by factoring, then by all means, go ahead and solve by factoring. So I know it says here to use the quadratic formula or factoring if you can do it that way. And then when we resume, I'm just going to show you the answer. I'm not going to show you the whole process because we did two together. All right, so you should get for part A that x equals -2. There's only one solution, and you could do that by factoring. And then for part B, you should get two solutions. And if you stopped before simplifying the radical, if you stopped here, I just want to remind you how to simplify radicals. The square root of 28 can be simplified because 28 has factors that are perfect squares. So if I factor 28, there are 2 factors of 2. That means I can simplify that radical. So I can factor out a 2 from the radical, and the 7 is stuck inside. Okay, if you need additional review about simplifying radicals, please let me know. If enough people want to review radicals in detail now, we can do that together. Otherwise, we might set up office hours. So simplified, your final answer should be -2 plus or minus the square root of 7, which is 2 real solutions. Okay. So when we're looking at our quadratic formula, what we've been noticing is that we don't always get the same number of solutions. Sometimes we get 2 solutions, sometimes we get 1 solution. And what determines whether we get 1 or 2 solutions so far has been the part underneath the radical. We said when that part underneath the radical, when b squared minus 4ac equaled 0, we had only 1 real solution. So what would happen if b squared minus 4ac was less than 0? What happens when I have the square root of, for example, -4? The square root of -4, that would mean 2 numbers that multiply, a number that multiplies by itself, I should say, to -4, right? We can say 2 times 2 is 4, but -2 times -2 is also 4. So what happens when we have a negative under the square root is that there are no real solutions. And so b squared minus 4ac is called the discriminant, because if it's positive, we have 2 real solutions. If it's 0, we have 1 real solution. And if it's negative, we have no real solutions. So let's look at that breakdown again. When we have our discriminant, b squared minus 4ac is positive. So that's, I've got negative b over 2a plus or minus a positive number over 2a. This is going to give me 2 solutions, or 2 x-intercepts. When I have negative b over 2a plus 0 over 2a, or I should say plus or minus, okay, well, 0 over 2a is just 0, so this is going to give me just 1 real solution, and importantly, that solution will be the vertex. Remember, this is our vertex formula. And then lastly, if our discriminant, b squared minus 4ac, is less than 0, then we have negative b over 2a plus or minus the square root of a negative number over 2a. Well, that is illegal. We cannot take that. It's not real. There's not a number that multiplied by itself gives us a negative number. And so we get no x-intercepts. And what that means is that our parabola does not cross the x-axis. Okay, but why can't we take the square root of a negative number? Why does that cause an issue? Well, this right here, square root of a negative number, is how we get what's called imaginary numbers. Imaginary numbers. So let's look at what are imaginary numbers. Oh, an example with the discriminant first. So first, we're going to talk about imaginary numbers in a second. To use the discriminant, we don't have to solve for x, right? We just want to know how many solutions there will be. So if I want to solve this without, or I want to know how many solutions, how many x-intercepts will there be without solving for x, all I have to do is b squared minus 4ac. So So I'm going to say A is 2, B is -3, and C is 7. Then I have B squared minus 4AC. Well, that's 9 minus 4 times 2 is 8. 8 times 7 is 56. That's definitely less than 0. When I have the square root of a negative number, I have no real solutions. If we look at part B, first thing we have to notice is that this is not in standard form, so we need to get all of our terms on the same side. Now, it doesn't matter if you move them to the right or to the left. I think most of you would instinctually move them to the right, or to the left rather. So I'm going to go ahead and show you what happens if I subtract the x squared instead. 0 equals -x squared plus 6x plus 5. Then I say A is -1, B is 6, C is 5, B squared minus 4AC, 6 squared minus 4 times -1 times 5. So that's 36. -4 times a -1 is +4 times 5 is plus 20. And that is positive. If it's positive, there are 2 real solutions. Now, the value that we get here, 56, will appear as we're calculating our answer, but this is not our value for x. Remember, x is going to be -b, b was 6, plus or minus the square root of that whole thing. So that's where the 56 will show up, divided by 2a. So we didn't calculate x when we found the discriminant. We just found out if there will be 1, 2, or 0 values for x. So in this case, there will be 2 values for x, but neither of them has to be 56. Okay. So for this one, I want you not just to find the discriminant, but to find the actual solution. So using the quadratic formula, see if you can solve this. Okay, now I'm not going to have you type your answer into Edpuzzle. I'm just going to ask you if you got a solution or not, because I want to go through this together with you. So the first step is to label our A, B, and C. And then we're going to substitute it into our quadratic formula. X is equal to -b plus or minus the square root of b squared minus 4ac all over 2a. So here we get negative of a negative is +3 plus or minus the square root of 9 minus 4 times 2 is 8 times 5 is 40 all over 4. So now we have 3 plus or minus the square root of -36 over 4. And then we get stuck because we can't simplify the square root of -36. So that's as far as we can go right now. But we know that there are no real solutions. So what is this solution that I just found? Well, because of this negative under the square root, this isn't a real number because there's no real number that when multiplied by itself gives me -36. So this is what we call an imaginary number. Now, imaginary numbers are part of what's called complex numbers along with real numbers. So think about real numbers has rational and irrational numbers. Complex numbers have real and non-real or imaginary numbers. So what is an imaginary number? Imaginary numbers are when we need a number whose square is negative. No matter what real number I pick, when I square it, it will be positive. So an imaginary number is a number that was discovered so that when we square it, it's negative. So the definition of an imaginary number is that I squared is -1. Definition. And the side effect of that definition is that we find that the square root of -1 is I. So we defined I so that its square is -1. And that way, when we take the square root of -1, we can call it I. Okay, so if I take the square root of a negative number, we can then continue calculating by pulling the -1 out from underneath the square root. So in our previous example, we had the square root of -36. We would break that up into the square root of -1 and the square root of 36. Using our rules for square roots, these are still multiplied, but then the square root of -1 is I, and the square root of 36 is 6. So we can say this equals 6I. Okay, if we can't simplify our square root, that's fine. We would just leave it under the radical. So the example given here, if I have the square root of -5, that's the square root of -1 times the square root of 5. And this part is I, so that's I times the square root of 5. Okay. We can also see that if we were to square the square root of -5, now up to this point we said anything squared will always be positive, but that's because we were only working with real numbers. So now if we have the square root of -5 squared, that's the same as I times the square root of 5 squared, which means that's I squared times the square root of 5 squared. I times the square root of 5 times I times the square root of 5 would be I times the square root of 5 times the square root of 5. So that's I squared times the square root of 5, but I squared is defined to be -1. So for the first time, we now have perfect squares that can be negative. Okay, so let's look at an example. If I have the square root of -12, and I want to simplify this using the imaginary unit I, the first thing that we're going to do is take that negative and separate it out. So this is the square root of -1 times the square root of 12. This is not the same thing as negative square root of 12, and we're going to talk about that in a second. Okay, so if I have the square root of -1 times the square root of 12, square root of -1 is I. The square root of 12 can actually be simplified. That's 4 times 3. So the square root of 4 times the square root of 3 gives me I times 2 times the square root of 3. Now we treat I as if it's an x. So if I gave you x times 2 times the square root of 3, we would write that 2x root 3 or 2 times the square root of 3x, right? Depending on how neat our square root symbol is. Since there's a risk of thinking that the x is inside of the square root when we write it at the end, we're going to write our I before the square root, 2I square root of 3. But just like with x, we wouldn't leave it in front of a number. And really the key here for imaginary numbers are going to be to treat I as if it's x. I works exactly the same way as x until we simplify. So we can take a negative out of a square root and it turns into an I. But if we have I squared, we don't want to leave it as I squared because I squared is -1. So we would simplify it to -1. Okay, let's try another example, part B. Square root of -25, we're going to write that as the square root of 1 times the square root of 25. That's I times 5. But again, just like with x, I wouldn't leave x 5. I would write it as 5x. So we write this as 5I. Part C, doing the same thing. Square root of -1 times the square root of 7. Square root of -1 is I. Square root of 7 cannot simplify. So we're going to leave the I in front of the square root because if I write it after the square root, there's a risk of thinking that it's inside of the radical, right? So we don't want to run that risk. We're going to leave the I in front of the square root. Okay, and then in part D, why is the square root of negative 64 different than negative square root of 64? Well, think about what question this is asking. This is saying some number times itself equals negative 64. Whereas this one says negative of something times itself is 64. So this is very similar to when we were saying negative 2 squared versus negative 2 squared, whether or not the negative is being squared. The exact same thing is happening here, but instead it's what is being taken the square root of. So if we have a negative inside of the square root, that's not the same as a negative outside of the square root. Okay, let's look at other operations for our imaginary numbers. So remember I said treat I the same as X. So we have 4 minus 3I plus negative 4 plus 3I. What would you do if it was X? 4 minus 3X plus negative 4 plus 3X. Well, we would combine like terms. So we're going to do exactly that. 4 minus 3I plus negative 4 plus 3I. Nothing to distribute because this was positive. 4 plus negative 4 is 0. Negative 3I plus 3I is 0I or 0x, imagine. 0I is the same as 0, so the answer here is just 0. For the next one, same thing. Pretend it's an x. 5 minus 3I. This time we do have to distribute. Plus 2 minus 4I. Combining like terms, 5 plus 2 is 7. Negative 3I minus 4I is minus 7I. And then we're done. As if it was an x. Okay, so for adding and subtracting, we treat it just like x. Same thing goes if we're multiplying. Treat it just like x. There's going to be one small difference. Same as x, except I squared is negative 1. So there's an extra step. When we get to the very end, when we normally would box our answer, we have to check if there are any powers of I. We want to change any I squareds into negative 1. So if this was an x, I would distribute. 3 times negative 5 is negative 15I. 3 times 2 is a positive 6I squared. Now, if this was x, we would be done, but it's not x. So I'm going to change that I squared into a negative 1. Negative 15I minus 6. And then notation-wise, we always want the I to be the last thing we read. So I'm going to rewrite this as negative 6 minus 15I. This is called A plus BI form. And that just means the term with I goes last. Okay, it also means if I have I in a fraction, I want to split my fraction, but we're going to talk about that in a minute. Okay, part B. We're going to do the same thing. What if it was x? If it was x, I would FOIL. So we're going to do that. Distribute our terms. 4 times negative 1 is negative 4. 4 times negative 2i is negative 8i. 3i times negative 1 is negative 3i. 3i times negative 2i is a minus 6i squared. Combine my like terms. Negative 8 minus 3 is negative 11i minus 6. And there's that I squared. The only difference between x is that I squared turns into a -1. So now I have -4 minus 11i plus 6. -4 plus 6 is 2 minus 11i. Remember, we want to write the I last. Okay. So powers of I. We said that I squared is -1, right? So I squared is -1. And I to the first power is I. What about I to the 0? I to the 0, well, we said any number to the 0 is 1. Same thing happens for I to the 0. So then this is I to the first. Then what happens with I cubed? Well, I cubed is I squared times I, which is -1 times I. So that's -I. Okay, but then what about I to the fourth? I to the fourth is I squared times I squared, which is -1 times -1, which is 1. So we're back to 1. And if I take I to the fourth times I, that's 1 times I, which is just I, but that's also the same as I to the fifth. And so we keep going around in a circle, I to the sixth, I to the seventh, I to the eighth, I to the ninth, I to the 10th. But the nice thing about I is we can go backwards as well. I to the 0 go backwards should be I to the -1. Well, what is I to the -1? It's 1 over I. If I go backwards again, that's I to the -2. Well, I to the -2 is 1 over I squared, which is 1 over -1, which equals -1. So when we're talking about I, remember I said simplify it so that there are no exponents. You should never have I raised to a power in your answer, because we can keep simplifying I squareds, just factor out I squared over and over and over again until the only thing left is a positive or negative I or a real number. We're going to do this together. So we have that A, oops, where'd my pencil go? A is 2, B is -3, and C is 5. X is equal to -b plus or minus the square root of b squared minus 4ac all over 2a. We said that's 3 plus or minus the square root. Remember, we got -36 over 4. And now we can say that this is plus or minus the square root of -36 is I times 6 over 4. 3 plus or minus 6i over 4. But we want to write it in a plus bi form. And that means that I should be last, but I should also be separate from our real part. So in order to do that, if we have a fraction, we're just going to write each term divided by the denominator separately, just like combining two fractions, except we're separating them apart. And then we can simplify each fraction. So now we have 3 over 4 plus or minus 3 over 2i, and that is our final answer for x. Okay, I'm not going to be super strict on the format of writing our complex non-real numbers right now. So if you write your I that's not in a plus bi form on an assessment, I'll give you credit for that. But we do want to start practicing writing our complex answers in a plus bi form, just because that's the standard way that we will write complex numbers from here on out. Okay. I have some practice for you to try. Some of them might be complex, some of them might be real, some of them might have two solutions, one solutions, or no solution. But make sure for these last three, you don't have to find the solutions. You just need to find the number of real solutions. So the answer for 5, 6, and 7 should be 0, 1, or 2. For each of those, there's only 3 possible answers, 0, 1, or 2. And it's not like each answer will be used one or anything like that. I could have all of them have 2 solutions, but you're not solving for X on those ones. Okay. If you have any questions, reach out to me. Otherwise, I will see you next class.